Hello everybody, I'm Lorenz from Microsoft, and today I am going to present to you the results of the packet loss concealment challenge that we did at INTERSPEECH this year. So first of all, what is packet loss concealment? Packet loss concealment, or specifically audio packet loss concealment, is the hiding of gaps in audio streams that are caused by data transmission failures in packet switched networks. Which means we have some audio stream, we packetize it. On the other side, we try to reconstruct the audio stream from the packets, but some packets got lost. We have gaps in the audio stream. All real-time communication systems need to solve this problem in some way. And the key point here is real-time, because there are more general audio in-painting techniques, but most of these do not apply here because we do not have future context. The receiving computer needs to output audio now, and usually we have limited compute because we have some end user device. It could be a phone, it could be a 10-year-old laptop, and the PLC has to run on that device. And deep PLC is just PLC, but done with deep neural networks. Now the question is, why do we want to do deep PLC? Why is this worth doing? Well, we have to do PLC. Like, packet loss is unavoidable. If you have a packet switched network, then it will experience packet loss at some point. And we have to fill that gap with something. Classical PLC causes distorted audio, and we can see that if we play these examples here. So first, the most basic imaginable PLC method, which is just fill gaps with nothing, with zeros.
LibriVox recordings are in the public domain. For more information, please visit LibriVox.org. Recording by Kane Mercer.
And then a PLC method that is actually in use. This is the PLC in use of Skype.
And in the dawn, all were asleep under their coats. Not far from them were 3 hobbled horses. One of them clamped.
So you can hear that even when PLC is being done with a technique that is in common use, signal processing based, you still have these weird distortion sounds. And in fact, distorted audio is, for us at Microsoft, is one of the top problem tokens in Teams calls. So when you get Teams, when you get the little survey at the end, when you select distorted voice, then you're one of a lot of people who do that. And that is often caused by packet loss concealment not being as good as it could be. So what can we do about it? Well, neural audio processing is now feasible. Compute is there, algorithms are there to actually process audio with neural networks in real time. So maybe we can exploit that to do better. Before we get to the meat of things, a quick aside about other means of preventing or mitigating packet loss. Two techniques very commonly used in codecs are a jitter buffer and forward error correction. First, the jitter buffer is a buffer that compensates for jitter. What's jitter? Jitter is the variance in network packet timing. So when a packet takes a bit longer than usual, to make sure that that doesn't cause a packet loss event, you keep a buffer of some length so that instead of a packet being a bit late causing packet loss, it just you have overall a bit more latency. How to trade off this latency versus packet loss, like what's worse for real-time communication, it's actually an unsolved problem. So if you have good ideas there, please consider publishing a paper or applying to Microsoft. Then a different technique that is used is forward error correction. Forward error correction sends redundant audio information in packets so that one gets lost. You can still use the redundant information to recover the audio stream. Forward error correction introduces some overhead into the stream, right? You need to send that redundant information, so you need more bandwidth. You also need a tiny bit more computation, and it also, again, introduces a bit of latency. Both of these are out of scope for the initial iteration of this challenge, however, maybe not forever, and I'll talk about that in the last slide. Now, we know about PLC. Why do a PLC or deep PLC challenge? Well, generally there has been very little publishing activity in this field. As neural audio processing, real-time neural audio processing is only just becoming really feasible. So there isn't really much publishing there. And what do you do when you have very little publishing, when everybody uses their own data sets, when everything's kind of scattered and hard to compare? Well, you do a challenge. That's what we did. And one additional goal we had with this challenge is also to gather a bit of training data so we can train an objective evaluation function that will help research in the future. And I'll talk about that on a later slide once again. Evaluation is also the keyword to get into the actual challenge. So the question is, how do you actually evaluate a challenge like this? And the answer is you have humans listen to audio for the most part. So we had two evaluation criteria actually. One was P808 crowdsourced CCR ratings, so comparative category ratings, where we had listeners who listened to a reference audio and distorted audio without an indication which was which, and were asked to rate on a 7-point scale from -3 audio B is much worse to +3 audio B is much better, with orders and everything reversed all the way, randomized, obviously. We do that because human rating, while expensive and time-consuming, is still the gold standard for audio quality evaluation. We have nothing better. The other criterion we used was the word error rate, as calculated using Azure Cognitive Services. We did this because we wanted to make sure that we also catch cases where maybe a word was left out or whatever, that human raters might not actually perceive as like an actual issue, but that are obviously, like in real life, if your packet loss concealment causes an entire word to be suppressed or causes a lot of silence to be output, that's an issue. So we also used the word error rate. From these, CMOS and word error rate, we calculate a final score, which is just the average of the CMOS, where we had normalized the 0 to 3 range to 0 to 1, and then the word accuracy, which is just 1 minus the word error rate. For CMOS, we heavily filtered for rater quality because we had a lot of quality issues where raters rated too many files or just gave the same rating a lot of times, so obviously weren't paying attention, failed test questions where we know the answer or know what we expect the answer to be. So for final, in the final value, the final CMOS scores, we had a confidence interval of 0.035. For word error rate, we excluded clips with untranscribable content, where untranscribable means either non-English or non-speech content for our speech recognizer. For the challenge, we provided multiple data sets. We provided a train and validation split initially, so people could train and evaluate models, and then a blind split in the last week of the challenge to actually rate the challenge. For the train and validation split, we provided clean reference audio, lossy audio with the zero substitution, as you heard earlier in this presentation, and a loss marker that says, okay, for each 20 millisecond segment, was there a packet loss or was there no packet loss? For the blind split, we only provided the zero substitution and the loss marker data. The data we provided is artificially constructed, but from real data. So we can't just use people's actual calls for this sort of thing, obviously. But what we can use is real packet loss traces, so that we can get the real packet loss patterns from actual calls. And we can apply that to public domain audio, in this case, LibriVox podcasts. And that's the data that we provided to participants. Just very quickly, how did we get to these packet loss traces? We started with a lot of traces from Teams, but most calls actually have pretty decent or close to no packet loss, but a lot do. So we just randomly sampled 10-second traces out of these large traces, each of which had at least one packet lost, split them into subsets that are different levels of hard. One normal, where the maximum burst packet loss is less than 120 milliseconds, a hard one where it's 120 to 320, and an aspirational set where it's 320 to 1000. Bigger than 1000, so more than 1 second burst loss, we discarded because no model can realistically do that, probably. We split these according to packet loss percentile, made sure to sample an equal amount of packets from each packet loss percentile to get sort of a good coverage of what the model might have to deal with, and then applied these to the LibriVox podcast segments, trying to not cut in the middle of words. Here, what you can see is a visualization of doing CMOS evaluation on the lossy data. So sort of if you do nothing packet loss concealment-wise, you just play audio with zeros, this is what you get. -3 would be very bad, and 0 would be basically perfect. You can see for the low packet losses, it's quite good still, because there just isn't much that goes wrong. For the high packet losses, there is a lot, and the higher the burst loss is, sort of the quicker you get to this everything is terrible zone. So now, given this data, this blind data, people had to fill the gaps as best as they could. They had to do it with low latency. The maximum allowed algorithmic latency was 20 milliseconds, split between frame size and look ahead as people liked. And it had to be real time on a 2.4 gigahertz or equivalent Core i5. This is relatively lenient requirements, but we didn't want to sort of restrict ourselves to just very tiny models. So these are the rules that we chose. So here are the results. So you can see that nobody quite managed to beat the clean reference, which maybe should be expected. But a lot of people actually submitted really good models. The first place was Kuaishou, second place Amazon, and for the third place we have Alibaba Incorporated and the Oldenburg University tied, all with really good models, and I hope that you will also have a look at their posters in this session. Earlier in my presentation I mentioned PLC-MOS. So one of the problems, as I mentioned, is that we have in audio is human rate evaluation is expensive. It's slow, and handcrafted standard objective audio quality metrics are generally really bad. So what's the solution? Well, you build your own metric, you do it in a data-driven way. We have a bunch of prior work there. We have AUC-MOS, DNS-MOS, and PLC-MOS is now our task-specific metric for PLC. It's trained to produce an estimate of human mean opinion ratings given audio data, uses a convolutional recurrent encoder architecture, and there's two versions, non-intrusive and semi-intrusive. On the challenge data, PLC-MOS actually had a Pearson correlation of 0.95 with the human ratings, and a Spearman rank correlation of 0.93, so not bad at all. And obviously, we hope to improve it with data from this challenge. So what were some issues that we had during the challenge that might provide guidance for future challenges? Well, one was that solid evaluation is, I've mentioned multiple times now, difficult. We had big quality issues with raters. So if you're doing a challenge, if you have things rated by a lot of amateurs, please do good quality control because it matters. And then we had relatively tight timing. So maybe the next time we do a challenge, we'll try to move everything a bit up, because this year it was quite the rush towards the end. Also, there were a lot of issues with modeling. And one such issue is illustrated here. So what we show here is segments of 20 milliseconds. And you can above is the lossy audio, and then below is the audio from one participant. And one thing you can see is that the model reacts before it should have enough future context to actually do that, because we only allow 20 milliseconds. This type of error is actually very common. We had 3 models that were disqualified because of that. So for a potential future challenge, one thing we want to do is get ahead of these common issues and ideally provide tools to detect it. We also want to provide a better PLC-MOS, and we're working on that right now, which will help PLC research in general. And of course, for next time, we will work on getting a harder dataset and tighter rules. People actually provided really good results this time, so obviously the logical thing is to make the challenge harder. So in conclusion, we, I think, achieved our stated objective. We brought people together who are interested in deep PLC. With this challenge, we've about doubled the number of published papers in real-time deep PLC. We saw a lot of papers with really interesting ideas. Please have a look at the other posters in this session and maybe also interact with INTERSPEECH. And we collected a bunch of data that we hope to improve PLC-MOS with. Thank you for your attention, and I hope you have a nice interspeech.